Oh, good evening, guys. This is Professor David J. De Los Reyes. Okay, I've got the new topic tonight. Okay, let's proceed. My new topic tonight will be lesson number 84 on my channel under the topic Integral Calculus. The subtopic is length of arcs. Length of arcs. Example of that one is length of transmission lines. How to compute for the length of a transmission line. It has something like that. So the application of this length of arcs is on transmission lines for electrical engineers. Okay, let's proceed. I will try to read the theorem. Okay, then we shall, what do we call this, analyze later on how we will derive the equations for taking the length of arcs under Cartesian Coordinate System. Okay, let's proceed. I will just read. The length of an arc of a curve is the limit of the sum of the lengths of the set of consecutive curves when the number of such curves increases without bound. The meaning of this, okay, I will try to erase this one. If this is the curve, the meaning of that, if we try to draw minute triangle lines on here, okay, and so on, the length of the hypotenuse of the resulting right triangle, small right triangles are actually chords. Okay, so if this is the arc and we are required to compute for the total length of the arc, the meaning of the theorem is that the total length of the arc will be the summation of the individual chords. Okay, so as you increase the number of chords, it will be something like this, you know. If you try to increase the number of chords, the chord will become smaller. Okay, so actually, if the triangle becomes smaller, the hypotenuse of the result triangle will be almost equivalent to the chord. You got what I mean? This straight line here is almost equal to the arcs if the right triangle is very small. So if we increase the number of chords, actually we are more accurate in taking the total length of the arc. That's the meaning of the theorem over here. Okay, let's try to draw the corresponding figure. We are considering for the meantime Cartesian Coordinate System. This is the y-axis, x-axis. The curve is actually the one in red, okay? And the equation of this is y is equal to a function of x. We got 2 points on the curve. This is the first point, and this is the second point. If from the second point we drop a vertical line, it got a side dy. Okay? If from the first point we will draw a horizontal line, meaning horizontal, it is parallel with respect to the axes. This is the horizontal line, parallel to the x-axis. The resulting right triangle should have another side dx. Okay, so if this is horizontal and this is vertical, this angle here is 90 degrees. It is this. Okay. From the resulting 2 points, okay, we got a curve. And the term for that one is actually chord. this arc here is curved. But if we try to enlarge the resulting right triangle, we will enlarge it here. The one in red is actually the curve, and the one in straight line is actually the hypotenuse. The hypotenuse. It is a straight line. But if this dx here in dy are too small, we could say that ds is approximately equal to the curve. You got what I mean? Right? The difference is very minute. That's why we could say that the length of the differential arcs ds is approximately equal to the curve. Okay? From the first point, it should have a coordinate. The second point, it should have a coordinate also. So the coordinate to the first point will be, the abscissa here will be x equal to a, and the ordinate will be y equal to c. For the second point, the abscissa is x is equal to b, this link here, the abscissa of this point. And the ordinate will be this one, and the ordinate will be y equal to d. It is from the origin up here. So actually, we don't have any more problem regarding the limits, because if we know this, the coordinates of this point here and the coordinates of this point, upon reaching the so-called integration process, we should apply the limit. That's the importance of these 2 points over here. Okay, let's derive the formula for taking the length of arc under Cartesian coordinate system. I enlarge this right triangle over here. It is not a right triangle, okay? Because the one in red is actually an arch, right? But according to the theorem, if this dy and dx approaches, you know, a very small value, almost zero, okay? If these are very minute, we could say that the resulting hypotenuse is equal to the curve. It is here. Okay? That's why I place it here. If dy and dx are very small, the hypotenuse is equal to the curve. It is this. The hypotenuse of the resulting right triangle will be equal to the curve if this dx here and dy are too small. Okay? So if they are too small, we could remove now the one in red. Right? What comes out? It is a right triangle, right? So this will now be the hypotenuse. Okay? But the hypotenuse will be equal to ds, the length of arc, differential arc. So using Pythagorean theorem, ds quantity square, the square of the hypotenuse, equal to the square of the adjacent side plus the square of the opposite side. Okay? Then dividing all terms by the square of dx. So ds quantity square over dx quantity square. Dx quantity square by itself will be 1. Dy quantity square is dy quantity square all over dx quantity square. Okay? Second power, we factor out. So this will be ds over dx quantity square equal to 1 plus second power, okay, this should be dy over dx quantity square. Then try to take the square root of both sides, or raise both sides of the equation to the 1/2. On the left hand side, these two here cancel with this. So what will remain will be ds over dx equal to, right hand side, it is not a perfect square for the meantime, we do not know the value. So it will just be simply the square root of 1 plus dy dx quantity square. Okay? But this is ds over dx. And again, multiplying all terms by dx, right? ds over dx times dx this dx cancels. So what will remain on the left will be differential length of arc is equal to the square root of 1 plus dy dx quantity square times dx. This is a general formula for taking the length of arc if we know the value of dy dx quantity square. But we should know also the limit. On the first one, the differential thing is x, right? So the limit should be abscissas. So under case number 1, if we try to integrate both sides, if this is dx, our limit should be abscissa. Okay, it should be from x equal to a, then to x equal to b. Because it seems the problem is asking for the length of the arc between this point here and this point. So the limit will be from x equal to a, x equal to b. That is case number 1. Okay. For case number 2, it will just be the reverse. Dy dx is actually the first derivative of y equal to a function of x. Whatever the given equation y equal to a function of x, dy dx will be the first derivative of this. And to solve for dx dy, dx over dy, take the reciprocal. It is 1 over dy dx. And this is actually dx dy. So under case number 2, if we are integrating with respect to y, the integral of differential s equal to the integral with the limit from c to d, okay? C to d. It will be the square root of 1. Case number 2 will be dx over dy quantity square times dy. The limit should be, if we are integrating with respect to y, our limit should be from c to d. So this is actually c and d. That is under case number 2. Actually, case number 2 was derived from case number 1. It is just the reciprocal. Okay, because actually we could derive this one. We start from here. Okay, instead of solving for what they call this dy dx, you take the reciprocal. That's why I place it here. Dx over dy is the reciprocal of 1 over dy dx. So actually, you could derive general equation number 2 from equation number 1 by just taking the reciprocal. So the important thing here is case number 1. The integral of the total differential arcs, total, equal to the integral from a to b of the square root of 1 plus dy over dx quantity square times dx. If this is x, this should be x. If this is y, this should be y. Easy, right? Okay guys, that's the general formula for setting up the differential length of arcs under integral calculus under the so-called Cartesian coordinate system. Okay, good evening, Los Angeles.